Hello, everyone. My name is Nathaniel BurnsWatson. I'm a first-year graduate student at UT Austin, and I'm here to tell you guys today about a technique for determining the host stars of planets in unresolved binaries. So to begin, let's just talk a little bit about binaries. So what you can see in the plot on the left here is on the bottom part of the x-axis, you have primary star mass for binaries, and then if you're an observer, there's spectral type on top. And then on the y-axis is companion frequency, which isn't quite the same thing as binary fraction, but for our purposes, they're basically analogous. What you can see is that as stellar mass increases, binaries become more common. And in particular, if you focus around the middle of the plot for the FGK stars, you can see that for sun-like stars, roughly half of them are in binaries. So we've heard a lot about trying to understand sun-like stars, and I think an important aspect of that is understanding that a lot of them are in binaries. And this matters actually because you'll hear more about this in Adam's talk tomorrow. But one thing we know is that binary stars have fewer planets on average. And so just from that alone, we can already say that planet formation is definitely different in some way in binaries. So talk a little bit more about binaries as planet hosts, particularly in the Kepler data that I'm working with. What you can see on this image on the left here is not Kepler, but it gets the point across that Kepler had really large pixels, and so most close binaries are unresolved. And so when we detect transiting planets in these unresolved Kepler binaries, we know there's a planet there, but we don't know which star it's orbiting. So how might we figure this out? Or why should we even care about figuring this out? One important reason is that the radius that we infer for this planet does depend strongly on or can depend strongly on the host star. And this affects the demographics of planet radii that we infer, especially the demographics of planets in binaries. And there are questions like, do more planets form around the primary star or the secondary star? And this has implications for understanding of planet formation in binaries. So my methodology so far has gone as follows. So I start with these Kepler light curves, and then I will assume, let's say, that the planet is orbiting the primary star, and so I correct for the flux contamination from the secondary star, or vice versa, so I'll end up with kind of two sets. And then I will fit transit models to both of these, and then do MCMC sampling to get posterior distributions for all the parameters in the model. And then I'm using astrodensity profiling, which we already heard about on Monday. And the idea is that using these parameters in my transit fitting model, I can estimate the density of the star that the planet is orbiting. That on its own isn't super useful, but work from Kendall Sullivan using a combination of photometric and spectroscopic follow-up has obtained independent density estimates for each of the stars in these binaries. So the idea is I compare the density that I get from my astrodensity profiling to its independent densities, and they should agree for the star that the planet's orbiting. So here's an example of what that looks like. This is KOI 1300. So you can see in the top left is the phase-folded light curve with the black points. The blue squares are the bin data, and then the red curve is the model that I fit. And that's assuming that the planet is orbiting the primary star. You can see the same thing in the bottom left for the secondary star. Then we go all the way over to the right. So what you see is that for those dashed histograms, those are the independent density estimates. Then the solid histograms are the density estimates that I'm getting from the astrodensity profiling. So if you look at the red histograms, those are for the secondary star. Those do not overlap at all. But for the blue histograms for the primary star, they overlap quite well. And so this is a case where we can pretty unambiguously say that this planet is orbiting the primary star. And we do get a new radius value. If you were to go onto Exoplanet Archive for KOI 1300, you would see a reported value of 1.2 Earth radii. We're getting that the radius for this planet should be closer to 1.7 Earth radii, which is a pretty significant revision. It's also quite different from the 3.4 Earth radii that you would infer if the planet was orbiting the secondary star. Now, we're going to narrow focus here to the radius gap, or potential lack thereof for planets and binaries. So what you can see on the left here is a plot of the radius distribution of Kepler binaries. On the top is just the uncorrected radius values that are reported by the Kepler team. The middle panel is the radius distribution that you'd expect if all the planets were orbiting the primary, and then the bottom is the same case if all the planets were orbiting the secondary. And the common assumption is that all the planets are orbiting the primary star, and if we were to look at that, there doesn't seem to be a radius gap for planets and binaries, which would be pretty significant. It would certainly have implications for how planets form in binaries. But this did assume that all the planets were orbiting the primary star, and realistically, that's probably not the case. Some of them are going to be orbiting the secondary star, and so that's going to change the actual distribution. So that's what I've been working on as of late. So the project that I'm focusing on right now is planets where if they're orbiting the primary star, they would be in the radius gap. They would be out of the radius gap if they were orbiting the secondary star. So far, I've done this for 10 total binary systems encompassing 15 total planets, including some planets that aren't actually in that radius gap range. And an important thing to note is that the binaries in this sample are all less than 2 arcseconds in angular separation, which is half the size of a Kepler pixel, so these really are just completely unresolved. And the kind of guiding question here is, are enough of these planets going to move out of this radius gap range when I do this analysis such that a gap reappears? So here's an example of the kind of results that I've been getting. The result that I showed you before was like a very clean one where we could very obviously tell that it's orbiting the primary star. But a lot of the results that I get are more like this, where it's not immediately obvious looking at it that we can say this planet is definitely orbiting this star. So in order to handle that, we've been using Bayes' theorem. And if you are not familiar, the basic idea is we've got what's called the Bayesian likelihood, which is essentially I can multiply those red histograms together and multiply the blue histograms together and normalize them such that I get some probability. But we can also add more information. We already know other things about the demographics of exoplanets, and so we can incorporate that into our analysis. You multiply them together, and then there's this marginal that we can't calculate, but it's just a normalization factor afterwards anyways. So what we end up with is a posterior probability that the planet is hosted by the primary or secondary star. So to talk a little bit more about the prior, one thing we know from the demographics of planets in single star systems is that small planets are a lot more common than large planets. And so what you see with the black histogram is just the single star planet radius distribution. But we don't want to make any assumptions about what's going on around that radius gap range where you see that dip, because it seems like there might not be a radius gap for planets and binaries. So I just kind of smoothed over that and fit that blue curve, which does a reasonably good job. But what this means is that if the planet's orbiting the secondary star, it's always going to have a larger radius than if it's orbiting the primary star. So our prior is always going to return a higher probability for the primary star than the secondary star. However, we do have observational and theoretical reasons for thinking that most of these planets should be around the primary star, and so this is actually kind of a natural way of incorporating that. So these are the results that I've gotten so far. The x-axis is the period of the planet in days, and then the y-axis is the planet's radius in Earth radii. Those empty squares are the uncorrected Kepler radius values. Those are what you would see on Exoplanet Archive right now. And then the circles are the corrected radius values, and they're color-coded by the primary host posterior probability, meaning that those solid blue points are very highly probable to be hosted by the primary star, and solid red points would be very probable to be hosted by the secondary star, and then gray points are somewhere in the middle. So for the 15 total planets I've analyzed, 11 seem to be more likely to be orbiting the primary, and 4 seem to be more likely to be orbiting the secondary, where more likely just means greater than 50%. And for the radius gap subsample specifically, 7 seem more likely for the primary, and 2 seem more likely for the secondary. So going back to that question of, do a lot of these planets move out of the radius gap range when I do this analysis? So far, the answer seems to be a tentative no. And so that would make it seem like the radius, we could say so far that there does still not seem to be a radius gap. Another point I will make is that for 5 planets, there is a greater than 90% probability that they're orbiting a primary. So those are pretty unambiguous cases. There's none that high for the secondary. The rest are all kind of 50-50-ish. So one thing to think about is the kind of behavior of the Bayesian likelihoods that we're calculating. If you look at all these distributions, you'll see that they all kind of show the same shape. They have a peak, and when you go to higher density values, it drops off very sharply. But at low radius values, it just has this tail that just kind of keeps going pretty much all the way out to 0. So what that means is that if the peak happens around the primary star density, then it's going to drop off really quickly, and it's not really going to overlap with the secondary star. And so the secondary star host can be ruled out. But if it peaks around the secondary star, it's going to tail off and overlap with the primary star. So primary star hosts can't really ever be ruled out. And so when in spite of that, the Bayesian likelihoods oftentimes show a pretty strong preference for secondary star hosts, but then it gets washed out by our prior that is biased against secondary star hosts. But even with all these factors kind of stacked against secondary star hosts, we are finding that they can't be ruled out in most cases. And so does this suggest that a lot of these planets really could be hosted by the secondary? That would be pretty significant if that were the case, because the common assumption is that all the planets are orbited by the primary. But, I mean, as you guys saw, the posterior distributions I'm getting are really broad. There's very low precision, and there could be unknown systematics at play. I've looked really hard to see if there are any in my analysis, and I haven't found any, but we did just hear a cautionary tale about limb darkening, so you never know. As a conclusion, we have found unambiguous primary star hosts for 5 planets so far, so this technique can work. Admittedly, the rest have been ambiguous. I think a longer-term goal is to perform this analysis for a much larger sample of planets, ideally order of magnitude larger. I could start to get statistics on primary versus secondary star hosts and start to actually compile a radius distribution for planets and binaries with this host star analysis done. And there are other questions that we could answer with a larger sample as well, like in multi-planet systems, are all the planets orbiting the same star, or is it some combination of both? Another thing is that our analysis is definitely signal to noise limited, and the best way to fix that would be to get more signal and less noise. And so I would love if I could get more epochs of these transits, and especially with higher precision photometry. Another thing we could do to get more conclusive results is to use other methods of inferring the host star and combining it with the astrodensity analysis that I'm using. So for example, we could look at the Kepler images and actually look for centroid shifts when the planet's in transit versus out of transit. And in multi-planet systems, we could also look for transit timing variations or lack thereof, and potentially other directions as well. So with that, I'll end it and open for questions.
Is impeccable. Questions. Let's start with the green checkered person.
Hi, Chris Lamb, University of Florida. Super cool project. Just a quick question. Could you comment on, for the sample of systems, binary systems that you studied, what's their separation like? Yeah.
Here's a plot with the sky projected separations, so it varies quite a bit. In terms of angular separation, they're all less than 2 arc seconds, which can vary quite a lot. Some of them are at the sub-arc second level.
Cool, thank you.
We have a question online.
How do you account for the likely non-zero eccentricities of these planets in your astrodensity profiling?
So currently I've just been fitting circular orbits. We have reasons to believe that binaries would actually circularize the orbits of planets, and also eccentricity does have an effect on the stellar density that you would infer, but it's a pretty weak effect at low eccentricities. You'd have to get to really high eccentricities before it starts to have a noticeable effect. So as of right now, I've just been fitting circular orbits.
In the front.
Just from my understanding, can you clarify that when you're calculating the radius of the planet, you just kind of choose whether it's orbiting the primary or the secondary, even if it's ambiguous? Is that true? So you're just like, okay, so if the posteriors show that it's orbiting the primary, then you're just like, okay, cool, we'll use the primary and we'll use that proper dilution, right?
Yeah, that's correct.
So then what's is it bad to just calculate both if it's ambiguous and see where it would end up in that case?
There are already estimates for what the radius would be in either case.
Okay.
I'm just using whichever probability is higher.
Gotcha.
Obviously, that's not the best assumption in these kind of ambiguous cases, but it's what I've been doing for now.
Gotcha.
We have a last, did you have a question? No? Yeah, see, there you go.
Great work and wonderful talk. I was curious to know, how do you get the temperatures and radii of each component star?
For the stars?
Yeah, how do you get the model densities for the stars?
Yeah, so I know I'm not the one who's done that analysis, but I know it's used a combination of resolved photometry using AO and also using spectroscopy on HET and using those constraints and stuff to model fit.
We have time for one final online question.
What percentage of Kepler-detected planets are hosted by unresolved binary systems that are thought to be single-star systems?
I know that there are about 200 of these unresolved Kepler binaries. I forget how many total Kepler KOIs there are, but so something like 1%, maybe a little less than 1%.
Cool. With that, let's thank him again.